So we know all strong acids and bases are equally strong in water. And we also know that all strong acids are going to dissociate completely to form H3O+, and all strong bases are going to dissociate completely to form OH-. Well, guess what, folks? The strongest acid possible in water is H3O+, and the strongest base possible in water is going to be OH-. So because H3O+ and OH- is going to be the strongest in water, when you have strong acids and bases that also produce H3O+ and OH-, guess what, folks? The water is going to exert what we call a leveling effect on the strong acid and the base. Now, what is a leveling effect? The leveling effect is a solvent's inability to distinguish the strength of an acid or base that is stronger than its own conjugate acid or base. So for water, its conjugate acid or base, because it's amphoteric, right, can be, of course, H3O+ and OH-. And so because these are also so strong, it's going to be very difficult to distinguish between anything that's also adding to acidity or basicity here. So in the previous part, we were trying to figure out the two types of effects that are going to help us understand a non-metal hydride. We said the electronegativity and the bond strength and bond length are going to help us figure out the strength, right? But it helped us understand that why HF is a weak acid, for example, because it definitely doesn't have the bond length, but we still weren't able to distinguish between the strong acids here. As you can see, there are no Ka values. It simply says strong acid, and strong acid. And that is because of the leveling effect. The leveling effect in water is going to make it hard to distinguish between any of these strong acids and also hard to distinguish between strong bases. So how do we distinguish between them? Well, what we need to do is find a solvent that has the ability to see or allow each of these acids to donate a proton. And when they donate a proton, and the extent of how they donate a proton, that's going to give us that acid strength. So what we did is you have to get a brand new solvent, and the brand new solvent is going to be pure acetic acid, for example. And instead of mixing it with water like we've done before, which causes that leveling effect, when we mix it with this weak acid here, it's going to act as a base. Yes, CH3COOH can act as a base. We don't dig into that for our course, but this is a detail of how it can. And because of that, it does allow, mixing it with acetic acid does allow for these acids to then donate their proton here. And based on how they donate their proton, a pattern came about to show us the level of proton donation, which is going to be the Ka value. So we saw a pattern was that Ka of the acid HI is going to be larger than the Ka of HBr, which is going to be larger than the Ka of HCl. So when it comes to acid strength, HI is a stronger acid than HBr, which is a stronger acid than HCl. And it's measurements from mixing it with a different solvent that helps us be able to get this pattern. Of course, again, we also can distinguish strong bases by dissolving them in a weaker solvent like liquid NH3 so that they have the ability to accept a proton, for example. So again, when we're thinking about how to distinguish our strong acids and bases, we have to get a brand new solvent outside of water due to the leveling effect.